I'm Huidong from China, and the topic that I will talk today is about the multi-platform software architectures for mobile augmented reality. And before the start, I'll introduce myself a little bit. I got the master and bachelor degree at the same university named University of Electronic Science and Technology of China. And I began to learn about the AR at the second year of my master, and do some work about the AR as my master thesis. And my research interest contains several aspects. The first one is the computer vision approaches and the human-computer interaction techniques in AR. At the same time, I'm pretty interested in to achieve some multi-platform implementation. Multi-platform implementation of AR system on different target mobile or embedded devices. And this is outline of my seminar. First, I will introduce the basic problem that we start, and then I will review some previous work, and later I'll give some results and test about the work that I have done. The first one. Well, there are three keywords in this topic title, and I need make a brief introduction or explanation about that. The first one is mobile AR. The mobile here refers to the AR application on mobile devices, such as the smartphone or tablet computers, which compared with the traditional AR application on desktop computers. The second one is multi-platform. The platform here does not talk about the hardware, but specifically concerning the software platforms, aka the different operating systems. And the last one is the software architecture. That will focus on the framework that help us to swiftly build and deploy mobile AR applications on different platforms. Okay. So the first question about the research is why we choose the mobile devices as the platform of the AR research, because the mobile devices had already been a common thing or common hardware for peoples, and there is a huge commercial opportunity for mobile AR applications. And at the same time, the mobile AR research and applications boom synchronously with the explosion in smartphone since 2007, because at that time the iPhone launched and new start. And most essentially, the mobile devices has already have enough capability to provide a smooth AR experience to users and stable, reliable, so it could be used in the real world applications. Anyway, all in all, it's full features for AR development. So we choose that one as our research platforms. And talk about the full feature for AR. We can check the hardware features of mobile devices and some significant improvement of the mobile devices capability during the past maybe 3 or 4 years. After the first year of the iPhone launched, the mobile device began to explode, and lots of new mobile devices have been launched at that time. But the capability is still limited. Like we can see from the table here, it's like for example the CPU, most of them less than 500 megahertz. But right now, today, we can get 1 gigahertz. Sometimes 0 core, so it's double speed. And the GPU, of course, at that time, I don't think there are lots of smartphones, even for the advanced smartphones, have no GPU at all. But right now, it's had a very powerful GPU supported, as well as the RAM and FPU, we can see the FPU is very important, because the FPU here is referred to the flow point calculation unit, which should support much more complicated calculations to the mobile devices. But at that time, has no FPU at all. But now they have, and as well as a kind of accessory like gyroscope or camera and the touch screen. In 2008, all of this has not installed or built in the smartphone, but right now they all have all these features. And there's an interesting thing about these components for mobile devices. The performance influencing factor, the order is RAM, GPU, CPU. So when we evaluate our result on different mobile devices, we should consider these factors at the same time. And you can use this one to decide which kind of which kind of cell phone do you want to buy at the same price. So it's pretty.
Assuming that if you increase the RAM,
the performance will be
more dramatic than if you increase CPU.
It's a little bit lower, but if you just increase the CPU, I don't think there will be big difference.
So if you double the RAM, you get bigger performance.
Yeah.
Increase CPU, but double CPU.
Yeah, something like that. Yeah. Okay. Sorry?
Is that in terms of computer tracking?
I think it's computer vision for the mobile devices. Computer vision calculation for mobile devices. It's general, but not so specific. Like, for example, if you have several Android phones at the same time, and you can order their capability without considering the optimization, of course. You can order their capability in using this principle, I think, basically. And next one, the software features for mobile AR. There are so many operating systems for mobile devices, but we just interested in these mobile device operating system, which have the following characteristics. The first one is consumer-oriented, which means it mainly focuses on the entertainment. Compare with the serious OS for business, like BlackBerry. You don't want to play games so frequently on BlackBerry, but you play games frequently on iPhone or Android. That's the first thing. And of course, the consumer-oriented cell phone will support the multimedia features like image, audio, 3D graphics rendering, and all of them. At the same time, if you want to put all your energy into a platform, you have to choose some operating systems which has an active community. Then you can get lots of help and lots of new stuff. At the same time, it had continuous updates. For example, the Windows CE, like Windows CE 5, Microsoft stopped the Windows CE 5 development, and if you put lots of energy on that you won't get enough or continuous support from the company itself. That will be a bad situation, which means you have to choose some kind of operating system which has a long-term support. Anyways, I think the choice would be some kind of most popular mobile operating systems. Here is some popular OS examples. Like first, of course, iOS. Second, Android. The third is Windows Phone, but it's not popular enough to do the development. And the last was embedded Linux system. Sometimes we consider it as kind of customized Linux. It's very popular, but most people don't realize how popular it is. We can see the PSP, the PlayStation Portable, which is a production of the Sony company. They use embedded Linux, and they have powerful aggressive calculations. So, at the result, I conclude all these popular OS to two main streams. divided by their capability of system API. The first and the most important one is the Unix Linux-based operating system, like embedded Linux, and the other one is Windows-based. So they have their special system API, which is incompatible with other systems. And we can consider the iOS or Android as the Unix Linux-based operating system. They have the same Linux kernel, so the system API is kind of compatible, most part of them. And here is a problem that we'll study. Because of the incompatibility of mobile OS APIs, we cannot compile the applications which is originally used for Android, then to transfer them to the Windows Phone directly. And because of that, the usability and portability of the code is pretty poor. And at the same time, the compatibility of the applications is pretty bad. So as a result, each new phone is kind of a new challenge for development. You will make lots of problems, like you will spend a long development period on this one small project, and after you finish that, you realize that the target platform that you can use this application is limited, and sometimes you got lots of bugs generated from the system level, so it's pretty difficult to debug sometimes. Yeah. And we will review some papers on the mobile AR, the software architecture of mobile AR. We consider in terms of the problem, there are several corresponding solutions. The first one is the most common one, Transplant. Programmers just modify the source code into different versions to adapt some different kind of operating system or target platforms. As shown in the figure here, you can see for the Windows Phone and for the Linux, they have a different version of source code, and then use the different compilers to get to the executable file, and then transfer them to the local binary code, and which can run on the target platforms. This is the most common way. There's a PhD thesis talking about this. Daniel, 2007, handled augmented reality. He presented a framework that, for the first time, allows to create the practical AR application on the mobile devices, and the software runs on a broad range of mobile devices, but it's not easy to achieve the multi-platform portability just using that architecture. And but the advantage of that architecture is the code and the architecture is optimized so for the special target, so it performs pretty fast. The program performs pretty fast and robust. And the second solution is the cross-platform interpreter. Like we can consider the Java virtual machine. They can JVM. They can enable Java code to run on but most popular mobile devices to achieve a kind of platform independent features. So as presented in the chart here, you just write down one source code file and compile use a Java compiler to the class file, and using this single same file, then you can deploy all the application to different platforms like Windows Phone or ARM Linux or other. And in the local environment, on the cell phone, the JVM will explain this class file, class code, and turn that into the local binary code. So what you need to do right now is just write down one source code and run several platforms. And the similar work, the kind of work in this aspect has been done by Django, a PhD, a master student of the lab. He developed the computer vision algorithm library using G2ME for mobile devices. And because of the efficiency of the Java code, the library has poor efficiency for tracking, like 2 FPS most of the time. But it has a platform-independent characteristic for most Java-enabled mobile devices. So you can install them on basically the most part of the mobile devices today. And this is our proposed architecture. We combine the cross-platform compilers and the cross-platform open source libraries, and got the both advantage of them. We use a native code, C or C++ instead of Java, to speed up the performance. At the same time, we built a virtual layer to construct a similar structure as JVM. Maybe you guys have noticed that there only one source code, which is pretty similar to the Java, but we use how it works. We use cross-platform operating open source libraries. We use the API of the cross-platform libraries to build the source code, and then we can compile them to different mobile devices. So with the help of the cross-platform open source libraries, we can get the unified API and for different mobile devices, and then use a compiler to compile the same source code to the target local binary code, which can run on different mobile devices. And we have mentioned two key elements in this proposal. The first one is the cross-platform compiler. We choose the GCC, the GNU compiler collection, which has contained lots of powerful, I think the most powerful cross-platform for compilers. And at the same time, we follow the rule of the iOS standard, like C99 or C++11, which will, all of the code for different platforms have the same standard, so it has better portability in most cases. And another one is open source libraries. It's very important to choose this because what we want to achieve is the mobile AR, and compare with the AR key elements like camera driver, frame buffer, or image processor or graphic rendering, we try to figure out is there any stable and reliable open source libraries. At the same time, these libraries is multi-platform. So we figure out these most of the mobile devices use the Video for Linux driver to capture the image, and we use the SDL. SDL here is a kind of simple direct media layer, which you can use very simple API to access the low-level hardwares like audio or 3D hardware for OpenGL or 2D video frame buffer. And the third one is very famous for computer vision is OpenCV. And now most of the platform like Android or iOS have the special version of OpenCV, so we can use them directly we can use them directly with the same API. And last one is a little bit special because we'll talk this later. It's climate. For 3D, we didn't use some common like PowerVX, OpenGL implementation, but instead of the climate, because the development board that I chose is a little bit special, just to have the fixed point calculation ability. So this climate support the fixed point 3D rendering, and the only requirement for this library is 16-bit linear frame buffer. So it's pretty easy to achieve this. Most of the mobile devices today have support this feature. You can see the kernel framework for the mobile AR.
Can I ask a question about?
Yep.
So is that hardware accelerated then?
Sorry?
Is the graphics library hardware accelerated if you use that?
Accelerated?
Yeah. So
no.
It's not.
It's just use the fixed point without any GPU or something. It's pretty fast for the low cost development board.
Okay, so
Yeah.
sort of if you don't have access to OpenGL, is that right?
Yeah. It's kind of here is an explanation. It's the Clemens API is very similar, very similar to the OpenGL ES, but it's still different. Here the proposed framework.
Can I ask a question?
Yep.
So why not just use OpenGL.ES? Which platforms you're looking at don't?
Because when I implement this this application, the development board that I've used, it has no GPU, has no FPU. You cannot find appropriate libraries or implementations of OpenGL ES on that. So I tried to figure out either any way that I can use to implement.
So this is all previous work, right?
Yeah. It's just kind of some
talking about the past, not the future. Right?
Have the future at the end.
No, I'm saying, but this is.
Yes. It will have some detailed explanation later. Here is the general framework about this. On different, this part is for to build the mobile AR applications, and this part is for to deploy, because you have to choose some desktop computer system to compile cross compile your mobile source code. There are several available GCC that you can choose on different, like you use the compiler on the Unix or Linux or macOS, you can choose the compiler here. And then if you just use the Windows, you can choose the compiler here. And for different targets, like the mobile Windows Phone, you use the compiler for Windows Phone on Windows. So then you can get the local binary code that can run on the mobile devices. In general, you just got one source code and you compile and got several different target platforms like Windows Phone or Linux Phone, like iOS, like Android or iOS. Yeah, that's. And this is just a general one, and I have more detailed.
So did you say iOS?
Yep.
Is that a Mac?
Sorry?
That's Apple, isn't it? Yeah, I don't think that's yours.
Because I write. Oh. I use Unix, Linux, so it's the iOS kind of further development of the Unix. So the API of the iOS in low level is compatible with Unix. At the same time, the Linux. Yeah. Here the whole structure. This part is for tracking. We use SDL. Oh man. Sorry. Okay. This part we use the SDL, OpenCV, all of the open source libraries to build and implement the tracking part. And here is the cross-platform compiler that I mentioned, which would construct a virtual layer that cover or hit all the details of the system API. So you can use the same source code, here, and according to them, you can get the final executable files on the target platforms like iPhone or Nokia 900 or something like that. And his part is the software architecture for common users. You can just you can build under this principle. You can build like software on different platforms like Windows, like Mac OS or Linux. That's it's too much to and now we'll give some introduction about my work readout. This first one is the implementations. Well, I use 1.5 years ago. I choose a very low cost and cheap development board here. The feature of the board are already listed on the left side. So you can see it's use ARM9. The frequency of the CPU is around 400 megahertz, and the RAM is small, without GPU, without FPU. And I not use the camera like the mobile for today. You use a very powerful built-in camera. I just use the USB camera, which will decrease the capture speed, because when you capture the image from the camera, you have to transfer the image from the RAM of the camera to the RAM of the board. So, and I use ARM Linux with a kernel version of display surface, and then draw some cube or something directly on that. But the API of that is pretty, I think it's pretty difficult or complicated. So I choose the SDL. You just use like 20 lines of code, and you can forward the image or anything else to the screen directly. Use the frame buffer structure. And the right part is the OpenCV. I put the OpenCV into this ARM Linux and do the detecting and the tracking test, and got the result there. The cube here. Just use the OpenCV and got the image, and directly use the frame buffer to show them on the screen. And lefty the Climate, because I have no GPU or FPU, so I have to choose the Climate here. But it works pretty smooth and fast on this low CPU keyboard. So I think it's pretty nice to apply the library here. And I draw a cube without anything else. Still use the SDL as the frame buffer to show all the image on the screen. And finally, I integrate the SDL, OpenCV, and Climate, and got the simple AR applications. Draw a 3D cube on the marker. That's the final result. And this is the final picture of that. I made the face for this. Still, you can see it's not tiny enough compared with mobile devices today, but you can do lots of things like customize your system from the system level, so you have more freedom to control your system. And this is the FPS result. I just load the OpenCV mode and draw the line cube. It will up to 5 FPS. But when I join the 3D cube, it will, the user limit, the FPS will decrease to 3 FPS. And after that, I do the internship here and have the chance to play the memo system on Nokia 900. And I want to test is the software architecture that I've designed is kind of multi-platform. So because the 900 have the GPU and have FPU and support the OpenGL, so I didn't. So the code is a little bit different. But so I decided to just use the tracking part of the OpenCV, and without any code change, I directly run this tracking test on the 900. So it's pretty nice because you don't need to modify your source code, and you got the same result on different mobile devices. And future work. So maybe I need to test the architecture on more mobile devices, especially the mobile phone, because the API of the mobile phone is pretty different, or we can say it's incompatible with the Linux or Unix-based devices. So it will be a challenge if we can achieve the same result with little or tiny modification of the source code and run a mobile AR application on that. And the second one is, of course, the optimize the system to offer better performance, and as well as the markless AR system implementation. And while we are doing the tracking, not only the computer vision part will help us to track. We can also use the gyroscope to offer error compensations during the tracking to get more accurate result. And the last one is the mobile devices have limited resources, not only the calculation resources, but also the interaction resources. Like we just have the little area screen. So how to operate the virtual object inside the mobile AR application will be a hot topic in the future. And there are several related work they have done. The first left part is the initial unit communicate with the serial port of the board that I have used. It achieved the gyroscope and accelerator, but I just the board is made by my classmate, and I wrote the communication part of this work to communicate, to get the data from the unit and reflect them in the software. But I didn't finish that on my board, so it's a little bit pity. And the right part is my idea about how to use the computer vision method to achieve some kind of interaction tool. Because originally I just want to use like kind of object like pen to get the top point or pin of the pen to get the 3D prediction and operate, like select or rotate or move the object. And I designed a marker. This marker, the special part of this marker is that you can get the 3D prediction information of the top point or other point. And while you are rotating this, the point is the algorithm here can still track the 3D information of the pin. So, but the problem here is too huge. You can see the size of my hand and the size of this tool. At the same time, it's not stable enough. So maybe later I'll do some improvement. And here's the summary. We proposed a new framework for mobile AR, and we will put more energy on this. And we prove the feasibility of multi-platform software architecture for mobile AR. that we can, and then we presented a prototype of mobile AR sample applications based on that architecture, and that's all the work that I have done about the mobile AR. So thank you. That's all.
Great. Thank you. A lot of stuff there, Huidong. There's all sort of materials.